Welcome back. A function f from a to b is called onto or a surjection if and only if for every element b in b there is an element a in a with fa equals b. That is, for every y there exists an x such that fx equals y. A function f is called surjective if it is onto. Give an example of a function that is neither injective nor surjective. Okay. Okay. So suppose you have two sets A and B. B has two elements, A has three elements. Pretend you have a function f which takes one element here, actually which takes all the elements here. Then this is not injective because three different elements went to the same element. So it is not injective. It is not surjective because this element never got any. This element is not an image of any of these elements. Okay. So this is a pictorial representation. Here is another example that you are familiar with. Fx equals x to the power 2. Okay. So I need to tell you where my domain and codomain is. I'm saying suppose f is from the set of real numbers to the set of real numbers. Yeah. Okay. In this case, notice f is not injective because f of -2 is 4 and f of positive is also 4. That is, two different distinct elements land in the same value on the right hand side. F is not surjective because negative numbers, say for example -1, is not f of any real number. You see, because f of a would be a to the power 2, which can never be equal -1. Okay, for any real number a to the second power cannot be -1. So -1 is not an image for any real number. So f is not surjective either. All right. Give an example of a function that is injective but not surjective. So here is an example, right? So suppose I take a function f. You want something that is injective but not surjective. So suppose I take a function f from the set of, let's see, positive real numbers to the set of real numbers. Okay, given by f of a equals a to the power 2, right? Now you see at this point it is injective because if a is not equal b, then a to the second power is not equal b to the second power. Therefore, f of a is not equal f of b. So, f is injective. But f is not surjective because of the same reason as earlier. -1, that's on the right hand side, is not an image under f. That is, there is no real number, positive or otherwise, such that f of a equals -1. A pictorial drawing for something that is injective but not surjective can be seen as follows. Simply say this is my set A and this is my set B. Okay. Pretend A has 2 elements and B has 3 elements. And my function takes this element here. I better draw the draw the point separate so you can see it better. So here is a function which takes one element here, another element here. The two elements are, when two elements are distinct, their images are distinct, so f is injective. But this element is not an image of anybody. So this function is injective but not surjective. All right. Now, give an example of a function that is surjective but not injective. So let's see. Let's draw another picture. You want something that is surjective but not injective. So suppose you have 2 elements in your codomain and 3 elements in your domain. Okay. Say this element went here. This element also goes here. And this element goes here. Then this function f is surjective because every element in B is an image of some element from the left, but it is not injective because look at that, 2 different elements are landing in the same image, so it is not injective. If you want a more familiar example, you can take f from the set of real numbers to the set of non-negative real numbers. Okay? Non-negative real numbers. F of x equals x to the power 2. Note, for every non-negative real number b, square root b is a real number. Therefore, f of square root b equals b, because what does f do? It squares your input. So, f is surjective. Okay? Every non-negative real number has some real number whose image my chosen number is. But f is not injective because, well, I can find 2 distinct numbers, 2 and -2, who have the same image, 4. All right. So this F is surjective but not injective. Give an example of a function that is both injective and surjective. Such a function is called bijective. Let's draw a picture of a bijective function. That is my set A and this is my set B. Bijective means two distinct elements have to land in two distinct images. So this lands here, this lands here, and this has to land in the third one. You see, every distinct pair of distinct elements land in distinct images. Moreover, if there is nobody here who is not achieved. Every element on the right hand side is an image of somebody in the left hand side. In a more familiar example, saying, suppose your function f is from the set of real numbers to the set of real numbers given by fx equals 3x plus 5. Well, you know this is a linear function. In other words, you are going to go, well, positive slope, so it's a rising line. Regardless, you can check that f is both injective and surjective. Okay, so it is an increasing function, strictly increasing function, therefore injective, and it is surjective because every real number on the right is an image of real number from the left. All right, so you take any, let's see a few examples. Understand it carefully. Let A be not equal to B, then 3A is not equal to 3B, and therefore 3A plus 5 is not equal to 3B plus 5. That is, f of A is not equal to f of B. This tells me when I have two distinct numbers in the left, their images are distinct. So f is injective. What about surjective? Take any number here. Okay, the right hand side. Then let's see, f of b fraction b minus 5 over 3. Let's see what it does. It's going to take my input, multiply by 3, add 5. So it's going to be 3 times b minus 5 over 3 plus 5. So notice what happens. This 3 cancels. B minus 5 plus 5 equals B. In other words, for every right hand side number, there is a number in the left hand side whose image under F is B. So F is surjective. Okay, so this function is both injective and surjective. Therefore, F is bijective. All right. So let's continue here in our next video.